particular video, we'll do a couple examples here just to help you understand density and pressure. The first one here, it says find the pressure increase in the fluid in the syringe when a nurse applies a force of 42 newtons to the syringe's circular piston, and that particular piston has a radius of 1.1 centimeters. So right away, I noticed that the radius here is given in centimeters, so pay attention to units as you practice. Alright, so let's go and crack this out. So here in the diagram, here is a force of 42 newtons that's being applied to the syringe itself. And the cross-section area has a radius of 1.1 centimeters. So here in the light blue, that is the cross-section area that we're interested in. So here I kind of list what's given here. Force being applied is 42 newtons, and then I'm going to go ahead and convert the radius of the cross-section area from 1.1 centimeters to meters. So to convert centimeters to meters, all you have to do is divide by 100 because there's 100 centimeters for every 1 meter. Okay. So here the problem says pressure increase. So really I'm not looking for pressure 1 or 2. I'm just looking for the change in the pressure here because it says pressure increase, suggesting that there's some sort of change. So here you notice in my work I have delta P for pressure, so the change in pressure is going to equal to the force being applied over a certain amount of cross-section area. So here the force is given to us as 42 newtons. But you notice I can do is I can break up area into pi r squared. This is a circular shape, so therefore the area of a circular cross-section is just pi r squared. So here F is given to us as 42 newtons, pi is a constant, and the radius here I'm just going to plug in 0.011 meters. I'm going to square that. So make sure you pay attention to units once again. Don't just plug in 1.1 centimeters, okay? Because then otherwise your units will be jacked up. All right, other than that, really, as you can see here, it's just plug and chug. It would just be 42 divided by pi times 0.011 meters square. And if you do that properly in the calculator, you will get a value of 1.1 times 10 to the 5th Pascal. Pascal being the appropriate unit for pressure here. Alright, so let's go ahead and do the next example. Here it says there are 3 liquids that will not mix together. That's poured into a cylindrical container, and it wants us to find the force at the bottom of the container due to these liquids. And the volume and density of these liquids are given. So here's a little visual for you. So here is the cylindrical cylinder, and then I'm just going to go from left to right here. So the first liquid holds 0.5 liters, and it has a density of 2.6 grams per centimeters cube. So here in blue is the 0.5 liters. This again, not drawn on a scale. This is just to help you visualize stuff. And the next item is in orange is 0.25 liters. I did my best to go about halfway between blue because blue is 0.5, orange is 0.25, which should be about half of blue. And then last but not least, the volume of the last liquid, whatever it is 0.4. So I'll draw a little bigger than 0.25. So this is 0.4. 0.4 is bigger than 0.25, which is less than 0.5. So as you can see, just to help you visualize here proportionally. Alright, so in order to find what the force is, we have to figure out what the weight is for all these darn 3 liquids. So let's go ahead and crack it out. Here's weight, W here for weight, aka the same as the force of gravity due to the water weight itself, or the liquid weight itself. Here's W2, here's W3. W once again stands for weight. So the definition of weight is simply mass times gravity. So here in the blue region, I just have weight of this blue liquid is m1 times g. Likewise with the orange liquid, which is be m2 times g. And then last but not least, the third liquid, whatever color you want to use, but here I just use purple, so it'll be m3 times g. But the mass of the liquid is not given to us, right? So if you look at the given information, the volume is given. The volume is 0.5 liters for the first liquid, and the density is given as stated, which is 2.6 grams per centimeters cube. So it's important that you pay attention in units as you practice these types of problems. So the first thing we're going to apply is the just generic function of density. Okay, density by definition is mass over volume. So the density of any substance is mass over volume. In this case, we're dealing with 3-dimensional shapes, so it would be mass over volume. So I'm going to go ahead and isolate for m. Why? Because in all of these weight functions, it's m1 times g, m2 times g, m3 times g. Well, the mass is not given to me, so I need to, and I should substitute out mass. So therefore, mass by definition is the density of the substance times the volume of that particular substance. So I'm going to swap out all these M1, M2, M3 for density times volume of that particular region. So in no particular order, I'm just going to go from blue to purple. Mass 1 is simply the density of substance 1 times the volume of substance 1 times the acceleration due to gravity. So you notice here G doesn't have a subscript because it's a constant. Okay, I'm going to go ahead and do the same with M2. M2, I'm going to substitute out for the density of substance 2 times the volume of substance 2 times G. And likewise with the third one. Okay, so now that I know all of the stuff here, the density and the volume of each of these substances given to me, right? Once again, the first substance that was given is 0.5 liters, that's volume. The density of that first substance is 2.6 grams per centimeters cubed. So I'd like to take this opportunity to point it out. This is in grams per centimeters cubed. You need to convert. So I'm just going to show you just one of the three conversions. So hopefully if you need to, practice all three in case you need to get better at it. So I'm just going to do this first liquid in blue. Well, the density of the first liquid is given as 2.6 grams per centimeters cubed, which is what I started with in my parentheses. However, I need to get everything to kilo and liters because that's the proper units here. Okay. If you want, you can actually keep it in centimeters and then you can go from centimeters to second square later. But I want to go ahead and convert everything to kilograms and liters. So I'm just going to go ahead and convert 2.6 grams per centimeters cubed, which is the density of the first substance given. And I want to convert that to kilograms per liter. So for every 1 liter, there's 1,000 centimeters cubed, which is given here in the statement at the very end of the problem here, in case you don't know the conversion factor, in case you haven't taken chemistry. Okay, so centimeters cubed is going to cancel out, but then I have grams. Well, I know the conversion factor is for every kilogram, there's 1,000 grams. So by doing so, I can cancel out centimeters cubed, and I can also cancel out grams. So the only two units that are left over is kilograms in the numerator and liters on the bottom. So really, 2.6 grams per centimeters cubed is simply 2.6 kilograms per liter. Why? Because the thousands will cancel out. So watch my cursor. You see that 1,000 on top? There's 1,000 there, and there's 1,000 on the bottom. That's also going to cancel out. So this is a super easy conversion factor. So if you want, practice the 0.8 and the 1 gram here. Okay. So now that I have the first one converted, I'm just going to go ahead and use that information. So the density of this particular first substance has been converted to kilograms per liter. That's 2.6 kilograms per liter. The volume, which is given in liters, hence I needed to convert from grams per centimeters cubed to kilograms per liter because the volume here is given liters. So the L here is going to cancel out. Okay, so as you can see, kilograms, which is mass, times meters per second square, which is acceleration. So mass times acceleration, which is give us units of force, which is newtons. So here, if you multiply across, you get 12.74 newtons. And I'm going to do the same for the next two substances. Okay, so here, if you convert properly the 1 grams per centimeters cubed to kilograms per liter, it would just be 1. And then times that by the volume given in liters, which is 0.25, and the acceleration due to gravity near the surface of the planet is 9.8, and you'll get 2.45 newtons. And then last but not least, the purple substance, whatever it is, the density is given to us as 0.8 kilograms per liter. Once again, I've already converted mentally here. And the volume is 0.4 liters, and then G is 9.8. So if you do that, you get 3.14 newtons. And you're almost done here, right? The question asks, what is the magnitude of the force at the bottom? Because it's at the bottom of the liquid. It's at the bottom of this cylindrical, shape. So you would have to just add up all the weight because all the substance weight is pushing down on the cylinder. So therefore the cylinder is pushing upward. All right. So to find the net force at the bottom, you would simply have to just add up all the weight. So instead of W1, W2, and W3, I just call it F of G1, F of G2, and F of G3, just so you know that they're all the same. So therefore, I'm just going to plug in, I'm just going to plug and chug. I already found all these values where I'm circling back and forth with my cursor. So the first substance is 12.74 newtons, the second is 2.45, and then the last is 3.14 newtons. So if I add all that up my calculator, I'll get a value of about 18.33 newtons. So and that'd be my answer for this particular video. Okay, all right, I hope that helps. Stay nerdy, don't be whack.